Welcome, everyone. Today we are exploring a transformative paradigm in computing, the Semantic Operating System. This represents a fundamental shift toward micro-module architecture, or MMA, specifically designed for agentic systems. Unlike traditional monolithic structures, MMA utilizes a network of interconnected, specialized modules that communicate through semantic understanding rather than rigid code. As illustrated by the complex web on this slide, this architectural shift allows for unprecedented flexibility and intelligence in how agents interact and perform tasks. Let's dive deeper into how this new foundation is shaping the next generation of autonomous AI. We are currently witnessing a fundamental shift in the architecture of computing, the evolution from traditional software to agentic systems. This transition is defined by the move from encoded logic to emergent behavior. In the traditional paradigm, illustrated on the left, control flow is rigid and human-authored. Developers must meticulously define every branch, loop, and conditional statement, creating a deterministic structure where the outcome is strictly constrained by the written code. As we move toward the model-centric approach shown on the right, code effectively becomes latent. Control flow is no longer hard-coded. Instead, it is inferred by the model in real time. This allows for emergent behavior, where the system navigates complex tasks through learned patterns and probabilistic reasoning, rather than explicit manual instructions. We are shifting from a world where humans define the steps to one where models determine the path, marking a new era of flexible, autonomous, and highly adaptive intelligence. The collapse of the interface surface represents a fundamental paradigm shift in how we architect software interactions. Historically, modules have been burdened by an expansive interface surface area, requiring developers to manually manage complex branching logic, orchestration, and repetitive type conversions. However, as we move toward a model-driven approach, this surface area dramatically shrinks. By requiring modules to expose only a core data schema, a formal contract, and a protocol, we allow intelligent models to infer intent autonomously. This process effectively absorbs the traditional overhead of routing and versioned RPCs, distilling the entire interaction into a streamlined, pure data protocol. The result is a more resilient and decoupled architecture, where the complexity of communication is handled by the system's intelligence, rather than through rigid manual code. Traditional microservice architectures, or MSA, carry a significant burden known as explicit orchestration. Because machines lack the inherent ability to infer intent, developers are forced to implement thick interfaces to ensure system reliability. However, this necessity creates a landscape where every single connection becomes a potential liability. As illustrated by this complex web of dependencies, the operational overhead quickly compounds. We find ourselves constrained by the rigidity of strict schemas and the persistent requirement to maintain backward compatibility across versions. Furthermore, the system demands the management of explicit error codes and the navigation of dozens of endpoints for even basic service interactions. This visual spaghetti of connections highlights the fragility and massive coordination effort required in manually orchestrated environments. Semantic boundaries and dynamic routing represent a fundamental shift in how we approach system design through micro-module architecture, or MMA. In this paradigm, we effectively flip the traditional stack. Interfaces are no longer rigid, hard-coded points of contact. Instead, they become semantic affordances that describe what a module can do and how it should be interacted with based on its underlying meaning. As illustrated in the diagram, this architecture centers on a single, unified schema that coordinates various independent capabilities. These capabilities, represented by the outer modules, are not linked by static paths. Instead, they are connected through semantic descriptions and policy wrappers. The policy wrapper ensures that every interaction adheres to defined constraints, while the semantic description allows the system to understand the context of the data being passed. The result is a transition from static, linear pipelines to fluid, adaptive processes. By functioning as a cognitive directed acyclic graph, or DAG, the system can dynamically route information and tasks. It evaluates the situation in real time, assembly lining the necessary capabilities to meet specific objectives. This allows the architecture to remain highly flexible, adapting its logic and flow to the unique requirements of every individual request. The elimination of glue code represents a significant milestone in software engineering. As models learn to understand and adapt to interface contracts, the traditional requirement for imperative logic to bridge systems is rapidly diminishing. This transformation is evident across three critical layers. In orchestration, the necessity for manually programmed loops and retries is being phased out in favor of autonomous execution. Within the realm of glue code itself, we no longer need to write manual JSON transformations or perform complex schema mapping. The model handles these data translations inherently. Furthermore, domain logic is being reshaped as hard-coded business rules are replaced by adaptive, intelligent decision-making. By removing these layers of manual overhead, we allow the model to manage the complexities of system interoperability, significantly accelerating development cycles. Reasoning serves as the universal adapter in this architecture, shifting the paradigm from static, code-based connections to dynamic, cognitive integration. Rather than relying on rigid scripts to link disparate modules, the model leverages its inherent reasoning capabilities to map schemas, shape inputs, and route data autonomously. This intelligence allows the system to recover from malformed inputs automatically, ensuring continuous operation without manual intervention. As illustrated, this reasoning hub facilitates 5 core functions. It handles high-level planning to coordinate complex tasks and manages routing to direct information precisely where it is needed. It also performs the vital work of shaping inputs to meet specific requirements and interpreting outputs to ensure they are actionable. Finally, through sophisticated error recovery, the model can identify and resolve inconsistencies on the fly. By using reasoning as the glue, we replace brittle, hard-coded logic with a flexible and resilient framework capable of handling unpredictable data and complex workflows. To understand the architecture of our system, we must first examine the anatomy of a cognitive atom. A cognitive atom is a micromodule that has been stripped down to a pure, deterministic capability. By design, it handles no extraneous logic beyond its core function, ensuring maximum reliability and modularity. As illustrated here, each atom is defined by 4 fundamental components. The input schema dictates the precise data structure required for operation, while the output schema defines the exact format of the resulting data. The capability description provides a clear, semantic definition of the module's specific function. Finally, the constraints establish the operational boundaries and rules the atom must adhere to. By isolating capabilities into these atomic units, we create a scalable framework where complex cognitive processes are built from simple, predictable, and interchangeable parts. This slide outlines the structural blueprint for a semantic operating system. This architecture represents a fundamental shift in computing by moving away from traditional imperative logic and replacing it with a cognitive pipeline graph designed for micro-module architecture. The stack is organized into 6 integrated layers. At the foundation, Layer 1 is the core model, providing the underlying intelligence for the system. Layer 2 consists of micromodules, which are the granular, specialized components that perform specific functional tasks. These modules are organized and managed by Layer 3, the registry. The orchestration of these components happens at Layer 4, the meta-controller, which determines the logic and flow of the cognitive pipeline. To ensure accuracy and performance, Layer 5 contains evaluators that continuously monitor and assess the system's operations. Finally, Layer 6 is the execution engine, the layer responsible for the actual deployment and running of the final workflows. Together, these layers create a robust framework for a more intelligent and semantically aware computing environment. The architecture of this system is built upon a synergistic relationship between the core model and micromodules, designed to deliver deterministic capabilities through adaptive planning. The core model serves as the central intelligence hub, responsible for the critical high-level tasks of planning, routing, and the construction of execution pipelines. Directly supporting this core are the micromodules, which are characterized as small, stateless, and observable cognitive atoms. By decoupling these specialized functions from the central orchestrator, the system can dynamically assemble and deploy targeted capabilities to solve complex problems with both precision and flexibility. The registry and meta-controller form a critical architectural pair designed to govern system behavior. At the foundation, the registry functions as a structured catalog of all available system capabilities. This information is utilized by the metacontroller, which serves as a supervisory agent responsible for enforcing organizational policy and resolving conflicts. As shown on the right, the metacontroller performs three primary roles. It validates proposed plans before execution, enforces established policies in real time, and manages the complexities of long-running workflows. Together, these components ensure that all actions remain compliant, coordinated, and aligned with system requirements. Moving on to layers 5 and 6, we focus on the evaluation and execution components of the system. This stage is critical because it introduces a layer of self-critique and hallucination detection before the execution engine processes the model's generated plan graph. As illustrated, the evaluators act as a checkpoint, meticulously analyzing the proposed steps to ensure accuracy and reliability. Only after this rigorous evaluation does the system proceed to the execution engine, where the plan graph is navigated toward its final outcome. This process minimizes errors and ensures that the final results are both high quality and verified against the initial goals. The migration of failure modes represents a fundamental shift in how we approach system reliability. As we move from traditional software development to AI-integrated systems, errors do not simply disappear, they transform. We are transitioning from the deterministic world of procedural code failures to a more nuanced landscape of recoverable reasoning failures. On the left, we see the classic pitfalls of software engineering: null pointers, type mismatches, and flawed branching logic. These are hard failures that typically result in immediate crashes. On the right, we see their modern equivalents. Misinterpretation of intent occurs when a system follows instructions but misses the actual goal. Incorrect routing happens when an agent misdirects context between components. Hallucinated schema semantics involves the system projecting incorrect meaning onto data structures. Understanding this migration is key to building resilient applications, as it shifts our focus from fixing broken code to refining and steering agentic reasoning. Because agents dynamically generate behavior, our safety mechanisms must evolve. We are moving away from rigid, hard-coded constraints toward a paradigm of dynamic policy and continuous evaluation. This framework for safeguarding thin surfaces is built on four critical components. Strict schema validation provides a foundational layer of structural integrity. Evaluator modules perform real-time assessment of agent performance and intent. Policy guards act as dynamic boundaries to ensure alignment with safety protocols. Lastly, traceable reasoning logs offer the transparency required for deep auditing and continuous improvement. Together, these elements form a comprehensive defense for the next generation of autonomous systems. As we transition into an era defined by advanced AI systems, the human role in engineering is undergoing a fundamental shift. We are moving away from the traditional practice of writing rigid, manual control flow logic. Instead, our focus is pivoting toward defining the boundaries, capabilities, and safety parameters within which these systems operate. As illustrated by the scale, the weight of engineering effort is now concentrated on establishing robust examples, constraints, policies, and test cases. These foundational elements have become more critical than hard-coded business rules and routing. By shifting our attention to these high-level constraints, we ensure that while the system possesses the flexibility to solve complex problems, it does so within a safe, predictable, and aligned framework. Our primary objective is no longer to dictate every individual step, but to architect the environment that governs how the system behaves. The cognitive microkernel represents what may be the cleanest separation of concerns in the history of software development. In this architectural paradigm, the operating system moves away from managing internal logic to focus exclusively on enforcing contracts and managing data flow. This structure is defined by three primary layers. First, micromodules act as the system calls, providing a modular framework for functional interactions. Second, data envelopes serve as the medium for kernel messages, ensuring that information is encapsulated and communicated through strictly defined protocols. Finally, the model functions as both the scheduler and the planner, providing the intelligence necessary to orchestrate tasks and manage resources. By decoupling the cognitive planning from the underlying execution environment, we create a system that is fundamentally more efficient, scalable, and robust.